giving me the opportunity to talk about foliations. So I guess my goal in these 3 lectures is to try to explain what I know about this question. That is, what do laminations and foliations tell us about the topology of 3-manifolds, which is a slightly longer version of the title. So in particular, what that means is if you have a 3-manifold which has some foliation in it of some sort, whatever sort it is, then what information can you derive about the 3-manifold as a topology of 3-manifold from the foliation or lamination that lives inside of it? So most of the time I'll be talking about codimension 1 foliations of 3-manifolds as foliations of 3-manifolds by surfaces. But I just want to spend a few minutes to talk about codimension 2 foliations, a special case of them. Actually, is the bottom line readable? The top isn't. Well, okay. So here's. Is that the problem? What? Do you know how to do it? Push the projector closer to the screen. Okay, that's great. So here's as soon as we have a 3-manifold that's foliated by circles, that means that every leaf of this foliation is a circle. Then there's a theorem of David Epstein, which says that if you have a closed orientable 3-manifold with foliation by circles, then the space is a ciphered fibered space. So actually in 72, I can see he needed a C2 condition. So what's a ciphered fibered space? Well, so what that is it's something like this. You just have a 3-manifold. So a ciphered fibering comes with, one way you think of it is you have a map from a 3-manifold to a surface, and the preimage of every point is a circle, and it has this following local structure. That is, you just take a generic point, like take a neighborhood about a generic point, like this orange neighborhood. And if you take the preimage, it's just going to be a solid torus foliated by circles with the product foliation. So this is just a D2 cross S1 with the product foliation. But then there's a finite number of singular fibers, which are denoted by these black dots. And so the ciphered fibered structure on these black dots, or on these neighborhoods, look exactly like this. You just the preimage of, say, this little neighborhood looks like, well, just take a D2 cross I and just give it sort of the product foliation by intervals, and then just glue the top disk to the bottom disk to get a solid torus with some type of rational twist to it. So for example, here if you just glue by sort of a 1/3 twist, then what happens is that if you take a sort of a typical fiber, well, whatever twist you glue, it's just a nice sort of rotation. So the core of the solid torus will just, when you suspend it around, it will just close up to a nice closed circle. But these other circles might wrap around. So for example, PQ is 1/3. Then typical circles, any other circle is going to wrap around the solid torus 3-to-1. So it's not exactly a fibering by circles, but it's almost, and except for this controlled manner. So Epstein's theorem, so if you have foliation by circles, that actually foliation is it's almost a fibration, it's a cyclic fibering. And once you know that, then you know a whole lot, because there's a whole lot of facts about cyclic fibers, fiber spaces. I mean, they were studied by, I guess first studied by Seifert around 33, and he actually classified such things up to fiber-preserving homeomorphism. And actually that's almost like a complete classification. There's this little issue of, well, if you have a 3-manifold, maybe you could cyclic fiber in a couple different ways, but it turns out these other guys in, I guess around 68, they showed that, well, except for a couple of manifolds that you can just enumerate, you could any other closed 3-manifold that cyclic fibers in a unique way. Well, let me just throw out a couple other facts about these cyclic fibered spaces. Thurston has the conjectural picture of the 8 geometries on certain 3-manifolds after they've been reduced in certain ways. And so these cyclic fiber guys appear as 6 of the 8 geometries. So sort of maybe a somewhat unusual way of stating Thurston's geometrization conjecture is that if you have any 3-manifold, either there's an essential 2-sphere, which means there's a 2-sphere that doesn't bound to 3-cell, or there's an embedded pylon-injective torus, or the manifold cyclic fibered, or it's hyperbolic. So anyway, and here's another little fact, which is that cyclic fibered spaces have, if they have infinite fundamental group, then the fiber itself actually represents at the level of fundamental group, it represents a Z subgroup, which is normal. So, and actually we have this theorem now that in fact the converse is true, that if you have it's a closed irreducible 3-manifold with an infinite cyclic normal subgroup, then the manifold itself is a cyclic fibered space. So here's a homotopy condition to decide whether 3-manifold has a foliation by circles. Anyway, that was this so-called cyclic fibered space theorem. I guess Casson Young-Rice and myself sort of put the last piece, but there was sort of a whole lot of huge contributions by Waldhausen, Scott, Mess, and a whole lot of other people. Actually. So that's all I want to say about codimension 2. My goal here is to tell you just a number of theorems about today I'm going to tell you classical theorems about foliations on 3-manifolds. Everything from henceforth will have been already published by 20 years ago. So I want to give you some idea what the theorems are and give you some hints as to the idea of some of the proofs. So now we're going to talk about, for the remainder of my talks, about codimension 1. So we have a 3-manifold that has a foliation by surfaces. And so in other words, there's these charts the manifold is covered by these charts, and locally you just see this little D2 cross I with just filled up by these little D2 cross points, and the various little building blocks fit together, so all these leaves fit together. So that's what a foliation is. Well, that's what a 2-dimensional foliation of a 3-manifold is. So, as far as I'm concerned, I think the first real theorem in the subject of foliations on 3-manifolds is this theorem of Alexander in 1924, which is, his theorem is that if you take a 2-sphere, which is embedded, say piecewise linearly embedded in R3, then that 2-sphere bounds a piecewise linear ball. So, that doesn't sound like a foliations theorem, but to me it's a foliations theorem because it uses foliations in a essential way to understand how this S2 lives. In particular, I mean, suppose you have an S2 in R3, and you think of R3 being foliated by just horizontal planes. And, well, if you just choose the coordinates in R3 right, then you can have every sort of local maximum and the various local maxima. I mean, there will be just a finite number of sort of local maxima and local minima, and they'll all occur at different levels. So the idea is, I mean, what was revolutionary at the time was to use basically ideas of Morse theory to understand this embedding of this two-sphere in R3. And it's especially revolutionary, in my opinion, because Morse wasn't really a mathematician yet. He hadn't invented Morse theory, but it's besides the point. So what's the idea? I mean, the idea is here's this two-sphere. So here's this two-sphere living inside of R3. And so what you do is maybe just look at a local maximum, which is, say, the lowest local maximum. And now you just kind of look at the surface and how it lives in the space. And you just see just below the surface, just looking locally, you just see a bunch of circles, and a little bit lower and lower. Eventually, you'll either come down to a minimum, in which case you can just see directly that this thing bounds a ball, or you'll run into a saddle point. And well, you could run into a saddle point in a couple different ways, but so one of them is you might run to a saddle like this. But then you could do like a little smooth or piecewise linear isotopy and cancel this saddle with this center. Actually, one thing, advantage, just thinking maybe about the lowest maximum or something, is that when you're pushing this thing down, it's not going to encounter any stuff in the middle here, because otherwise you run into another maximum. That's just a little technical point which you could ignore. But so the point is, you just run this guy down. If he runs into a saddle, well, you can cancel him, or maybe you run into a saddle like this, in which case, well, by an induction argument, you know that so this part, one side or the other of this, both actually, of this two spheres could be standard because you just kind of cap this thing off, then it's a two sphere of fewer local maxima and local minima. So if you see this type of thing, then basically this, you can just by induction kind of suck this guy in, and again you get a picture with fewer tangencies. Or you might have this situation where this saddle somehow in some sense touches this, is connected to this maximum in two different ways. So when you push down the center to get to the saddle, suddenly you've got like the rim of a volcano. And well, if you got one of those guys, then you can, if you got one of those guys, then you just keep pushing and see what happens. And well, there's again sort of similar type of situations. I mean, when you push down a little further, you might run into a little local minimum here, and then pushing the whole bit down, you've canceled a lot of extremal points, or you might run into a saddle here, and when you push down below the level of the saddle, you'll be still left with a saddle, but ultimately you would have canceled this maximum minima, or again you might push down, now you'll get like a double volcano rim or something. Anyway, just a little analysis like that. So eventually you could just standardize the embedding of the two-sphere in R3, and a standard one bounds a ball, so the original one does. So this is, to me, a theorem of foliations, because you have the foliation there, and the foliation is guiding you to tell you what to do. So, right, and and this type of argument is just comes over and it comes up. I'll just superimpose this, guys. They just come up all the time. Well, let's do this one here. So, right. So here's, okay, so I guess in some sense classically the theory of foliations maybe began with the work of Rabe and Erisman. In particular, there's the famous Rabe foliation of S3, which, I mean, so this is the 50th anniversary of the Rabe foliation. And so here's the Rabe foliation. So you can imagine, here's like the interval cross R. So here's here's a foliation on the interval cross R. It's this infinite strip. You can see this. There's these two lines over here. I mean, it's a foliation by lines, but it has this nice symmetric pattern. And if you just sort of notice it has two symmetries. One sort of across the core, and one just by just translation, by just these little translations. So you can imagine taking this thing and spinning it around. So now you get a foliation on D2 cross R, where now these two boundary circles have become an annulus, sort of an infinite annulus. And meanwhile, these guys over here, so when you spin them around, become planes. And the end of the plane is out here, and it sort of comes around like this. Or another thing you could do to this guy is just mod out by just some discrete z acting on this z translation. And then you get a foliation on the annulus. So this is what's called the Rabe foliation of the annulus. Well, in any case, if you get this cylinder, you can mod out by a z action and get a foliation on the solid torus, or you can spin this guy however you prefer. And the upshot is a solid torus whose interior is foliated by planes. So this is this Rabe foliation. Whoops, this is the Rabe foliation on D2 cross S1. So it has the property that its boundaries are torus, and the interior each is foliated by each leaf of the interior is a plane, and it's a foliation on the solid torus. Now, there's a little fact that the S3 can be gotten by just taking two solid tori and gluing them together. I tried to draw it here. I haven't quite done the gluing yet, but you can think of here's one solid torus on the inside and one solid torus on the outside. So if you take two solid tori and glue them together, you get S3. So then you can get a foliation of S3 by just foliating each solid torus of the Rabe foliation and then gluing these solid tori together. So this foliation has a single torus leaf, and the interior is foliated by these planes. So now, a variation of this theme is a theorem of Licorice and Zishang, which says that any closed orientable 3-manifold has a codimension 1 foliation. So Rabe did it for S3, but it turns out that using that idea, you can just foliate any manifold. So here's how to do it. So a little fact, well, a big fact, is that if you're given any manifold, any closed orientable 3-manifold, can be gotten from the 3-sphere by just taking the 3-sphere and just drilling out a bunch of solid tori. Imagine these thick ropes, just drill them out, just remove them from S3, and then take solid torus and just re-glue the solid torus back again. Now, there's a lot of homeomorphisms of the torus to itself that are not homotopic to each other. So there's lots of different ways you can re-glue in the solid torus, and that's called surgery. So the fact is, any 3-manifold oriented could be obtained by surgery on a link. And the theorem of Alexander says you can make that link into a braid. So what you can imagine is that here's here's this braid which is living really close to the core of the RAID component. So it's just the braid is sort of right through the middle here, and it's right transverse to the foliation. So at level 2 dimensions, you see the sort of component sort of going through like this. Then you can do this operation of called tabularization, where you just basically drill out a neighborhood of this curve, and then perturb the foliation, so that to get a foliation of a manifold with torus boundary where these guys are leads, and you see the leads spin around. Actually, this two-dimensional picture, if you just sort of spin it around across S1, I mean, just rotate this picture around, you'll get really a three-dimensional picture. So then and now the act of surgery, fill in by filling in with this a RAID component. So now we see that every 3-manifold has a codimension 1 foliation. So usually this type of theorem is like good news, bad news, because if every object you can do something to it, means that something operation is maybe just too flabby to derive useful information. So maybe codimension 2 really, codimension 1 doesn't say anything. But we'll see, it really says a lot. So one thing important to understand, so the central idea about foliations is this idea of holonomy. So what's holonomy? Well, suppose you have some curve, gamma, that lives in a leaf. So here's this curve. Gamma. It's this black curve. Now, I'm drawing this as a two-dimensional picture, but so you can imagine, you have a one-dimensional foliation of, say, a surface. But, you just maybe cross this with an interval to get a sort of logo picture. So here's a little point on this curve, and there's a foliation, so there's a nice little chart here by these little intervals, and this point has a little chart, and so this curve is compact, so there's a finite number of charts that cover a neighborhood. So what you notice is that if you just take this first chart and second chart, if you just start here, if you're really close to this curve gamma, you walk along here, and you wind up the end of this chart is the beginning of the next one, and you can walk along here and walk along here. So if you're really in close, so if you're just a little bit off of this curve, you can still just parallel to someone walking along the curve, you can sort of walk along this leaf, and the upshot is you get a little map whose domain is just a little transverse interval, and it's mapped to another little transverse interval. It might be mapped inside of it, maybe a little bit outside, but if you're really small to start with, you won't pop out of the original chart. So Erisman, this idea of these local maps, this is the idea of holonomy due to Erisman, and he noticed that given a leaf, there's a map from actually the fundamental group of the leaf to germs of homomorphisms of the interval, which -1, which fix the origin. Actually, this idea of holonomy is just an idea central to 3-manifolds any codimension foliation in any manifold. Anyway, but what's really important is that if you have a curve in a leaf which is homotopically trivial, then this guy has trivial holonomy. So in fact, there's a little more general theorem due to RAID, which is that if you have a compact leaf, and suppose this map into germs of the interval is trivial, then that means that the foliation restricted to that. That means we say that leaf has trivial holonomy, and Rabe's stability theorem, says if a leaf has trivial holonomy, then you could find a little neighborhood where with the foliation is the product foliation. So if L is this leaf, and then there's a little neighborhood U, so the L restricted to U. I mean, U is the form L cross minus 1, 1. F restricted to U is just the product foliation. So, right. Actually, I should say, having drawn this picture here, you notice that there's a transverse interval here that parameterizes this foliations chart. And this one also has a transverse interval, which parameterizes the transverse direction. So you can compare this transverse interval to that one, and you get a map from like a piece of an interval to a piece of an interval. And you could talk about sort of the differentiability of that map. If all those little local maps are, say, of C2, well then you'd say that's a C2 foliation. If they're all analytic, then it's still analytic foliation. So, right. So, right, and then there's this theorem of Rabe. Here's another. So here's the first theorem that says if you know something about a foliation, then you could say something about the manifold. So here you have a foliation on a closed or animal 3-manifold, and you have a 2-sphere leaf. Then you could actually say something about the 3-manifold. You know exactly what the 3-manifold is, and you know exactly what the foliation is. It's manifold itself is just S2 cross S1, and F is just the product foliation, just the foliation by S2s. So somehow by this other stability theorem, the first Rabe stability theorem, just having an S2, it has a trivial fundamental group. So there's a little open interval of S2s about it. But actually, Rabe says that if you have these S2s, then actually there's actually a closed interval of S2s about it. I mean, these limit of S2s, which head off to the end of this open interval of S2s, actually limits to an S2. And so therefore you get that leads to an argument showing that you have the product foliation. So here's another theorem, Heffliger, 1958. So he says if you have an analytic foliation on a 3-manifold, well, then you could just conclude that the 3-manifold already has infinite fundamental group. And not only that, but if you have a curve transverse to the foliation, so here's this curve which is sort of whipping around the manifold, and if it just always transverse to the foliation, that's going to represent an element of infinite fundamental group. So let me try to give you a hint as to why Heffliger's theorem is true. So we have this foliation, and suppose we have a curve transverse to the foliation. I would like to show that curve is homotopically non-trivial. Well, if it's homotopically trivial, that means that the curve, could be extended. The curve into the manifold could be extended to the map of the disk. So there's an immersed disk in the manifold which spans this curve. And now you look at this disk, and this disk, we just maybe do a little homotopy to make a general position with respect to the foliation. So you have this foliation. So you have a singular foliation, that is the induced foliation of the foliation induced in the disk by the foliation in the manifold is a foliation with singularities. But one thing you do know, since the curve is transverse to the boundary, is you know that this foliation, it's transverse to the boundary. So you have a foliation transverse to the boundary with some singularities. So by the Poincare-Hopf index formula, this foliation is going to have some singularity of positive index. So let's call that singularity x, and so that's going to be a tangency of the immersed disk and the foliation. So you just ask yourself, well, what's the possibility? And it turns out the only possibility is that a little neighborhood of x is going to be just a little local maximum. That's the only way you get something of positive index. And now you look at that and say, the little maximum, I mean, it's all going on in a foliations chart, so I see this maximum, and the foliations are slicing through this disk in circles. So I have a little bit of information. Here, I see this point, there's this foliation by just parallel circles. On the other hand, I know this foliation is sort of coming into the boundary of the disk. So, anyway, what you can do is just look at sort of this circle and just, well, this circle either has trivial holonomy or not. And if it doesn't, well, you can just get bigger and bigger circles. And Hefliger says the limit of compact leaves is compact. So basically, you take sort of a maximal circle out here. And, well, if you're not very lucky, that circle might maybe hit another singularity. It's not something to worry about. Let's not worry about that. So if you don't, so what happens if you take a maximal circle is you'll see that this maximal circle, well, you'll see a curve where on one side they'll have trivial holonomy, because that's coming from sort of circles coming on this side. On the other side, there'll be sort of non-trivial holonomy. But that's a contradiction to analyticity, right? Because one thing we know about analytic manifolds, analytic functions, is if you have a function which is constant in a little neighborhood, it's constant globally. So here's a little germ of a map of an interval, and it's locally, it's constant on this half, so the whole thing better be constant. That's a contradiction. So that's the idea of Hefliger's theorem. Now Novocopt took this one big step further. So this is Novocopt's theorem, and he showed that if you have a closed orientable 3-manifold, say a codimension 1 rabless foliation. So rabless means no rabe components. So there's no part of the 3-manifold which is foliated, which is a solid torus with a rabe foliation. So under the hypothesis of rabless foliation, then every leaf injects at the level of fundamental group into the manifold. And not only that, if you have a curved transverse to the foliation, that represents an element of infinite fundamental group. And he also showed that pi2 of the manifold is trivial, or the manifold is S2 cross S1 with the product foliation. So let me just make a couple remarks. I'll just give you the hint about Novocopt's theorem. And one remark is actually Rosenberg a few years later showed improved pi2 being 0 to showing that m in fact was irreducible. That is, we're ignoring the S2 cross S1 case. If it's not S2 cross S1, then m is irreducible. In other words, every 2-sphere bounds a 3-self. And basically the idea is, if you know Novocopt's theorem, or at least you know its proof, and you know Alexander's theorem, then you just run Alexander's argument. So you have this 2-sphere living inside of this 3-manifold, and then you see a center, and just kind of push it, try to isotope it away. And, well, you might run into a problem, but that problem is basically handled by Novocopt. And actually, this is even proved a little further by Palmeira. He showed actually that the universal cover of a rabless manifold with rabless foliations are 3. So I want to give you the idea of the proof of Novocopt's theorem. So let's look at part 2. Just like Hefliger said, if you have a curved transverse to a foliation, then it represents an element of infinite order if the foliation is analytic. So let's compare the argument here. So here's this curve, gamma, transverse to the foliation, and suppose it's homotopically trivial. Now this is sort of a really nasty point in Novocopt's story, but just to give you the idea, that's what I'm trying to get across, suppose this guy is homotopically trivial and bounds a nice embedded disk. Maybe in reality the disk is immersed, but just to be embedded. So just like with Hefliger, you look at the induced foliation on this disk. And I mean, maybe if you're really lucky, you'll see the foliation will look like this. Now, what Novocopt does is take the whole mechanism sort of one step further by just, let's say, it says, look at this disk and look at actually living inside of the, let it live inside of the 3-manifold. So here's this disk. Now let's see, what does it really look like inside of the 3-manifold? Well, right at this local maximum, we see, remember, we knew what the local maximum picture was. We did. And it's just like a little local maximum in a chart. So when you're really close to this tangency here, you'll see these each of these curves are going to be on little disks. Now here's a nice embedded disk, and by RAID, if you have a little embedded disk, disk is trivial fundamental group. So it has a little a little neighborhood which is foliated by disks. So you can just take this disk and try to push it out, and try to, you have all these circles in here, and try to cap each of those circles by disks. Now, a priori you might think, well, okay, I'll just push this disk out, and just in some finite time, I'll learn that this purple curve bounds a disk. I mean, maybe he'll bound a disk. It's the limit of all these other disks. Well, that can't happen because this curve has non-trivial holonomy on it, and we know by Erisman, curves with non-trivial holonomy represent non-trivial elements in its leaf. And if this guy was actually bounding a disk, we'd be bounding a disk in its leaf. See, there's its leaf that it lives in. So somehow you just for this holonomy argument, you can't just push this disk out, and just go. You can't just push it all the way out. So what happens? You push the disk out, and the disk starts taking up more and more space. And the only possibility is, because this manifold has basically a finite volume, is that this tube kind of runs into itself. It starts here, you get bigger and bigger disks, and eventually the nose of this guy, this disk, is just going to be the full disk at a lower level. And anyway, but nevertheless, you still can just build up these disks and bigger, and somehow you can take the limit, and you'll see a torus bounding a solid torus, and here's this rate. I really sort of oversimplified this whole argument discussion, but I wanted to give you an idea of how you could see a RAID component coming out of a null homotopic curve. So, right. So, right. So let me tell you some other theorems about. So here, I'm going to state some other theorems. So these are theorems which say, well, if foliation has such and such property, then you have maybe know something about the manifold. So here's Saxtetter's theorem, and he says that if you have a foliation, C2 foliation of a 3-manifold, and foliation has no holonomy, then so it's a codimension 1 foliation, then actually this is a codimension 1 theorem. Well, okay. I've stated everything today in terms of foliations on 3-manifolds, but some of these theorems are really theorems about codimension 1 in any dimension. But just for simplicity, I'm just stating all in terms of 3-manifolds. Has no holonomy. Then his conclusion is that there's a closed non-singular 1 form which defines the foliation. So in other words, the tangent planes come from the kernel. I mean, you have this one form, you look at the vectors that are killed by the one form, and those are two-dimensional planes, and they give you, they define the foliation. And Rosenberg and Sondale used that to show that if you had a C2 foliation of a closed three-manifold by planes, this guy's closed, then the manifold itself is a three-torus. And actually, for them, the C2 is, Saxe-Stetter's theorem is not right for C0, for example. So these guys anyway use this Saxe-Stetter, but Imanishi actually gave a C0 proof of this theorem. That is, you have a foliation of three-manifold by planes. The transverse structure is only C0. Then you can show that the manifold's three-torus. And here's another theorem that if you have a foliation defined by a closed one form, and these are the foliations that have no holonomy, I mean the ones that come out by Saxe-Stetter's theorem, then actually you could perturb the foliation a tiny bit and show the manifold actually fibers over the circle. So the manifold has this fibration by compact surfaces, which are fibers of fibration over the circle. So I think these are really nice, really good theorems. So, right. So here's a little fact about foliations. So suppose you start with this basic fact's really two little facts. So you have a foliation of a three-manifold with pi1 injective leads. So when you pass the universal cover, then since the leaves are pi1 injective, then each leaf being universal cover, well, each leaf is going to lift up to its universal cover. The universal cover of a surface is a plane. So, right, I mean, if the leaf didn't lift up to its universal cover, then there would be some fundamental group left which would die in the manifold. So, in the universal cover. So if you have foliation by pi1 injective leads, for example, the foliations that come out of the rainbow foliations by Novocopt, then the foliation in the universal cover is a foliation of a simply connected manifold by planes. And it turns out that the space of leaves of that foliation is a simply connected one manifold. So the point is, here you have a simply connected manifold, and it's foliated by planes. And so if you look at a little chart, then you'll see, little charts like a D2 cross I. So there's little transverse intervals give you the basis for the one manifold structure, and all those little transverse intervals, you can sort of put them together. And using the simple connectivity of the manifold, it's easy to, it's a little argument to show that the space of leaves of the foliation is a simply connected one manifold. So maybe I should have said, what's the space of leaves? You take this foliation, you have a foliation, and you can imagine you have a foliation of a manifold. And just take the quotient topology, where you just decree that each leaf is just collapsed down to a single point. So you have this foliation by plane, and just collapse each plane down to a single point. So when you collapse each plane down to a single point, that's going to reduce this simply connected manifold. And the quotient will be a simply connected one manifold. But it's really interesting that it's likely to be non-Hausdorff. Now, there's this remarkable theorem about non-Hausdorff simply connected. Well, there's a remarkable theorem about simply connected one manifolds, which is, well, it's due to Kaplan and sort of maybe a different language due to Heffelger-Rabe. It's just the Heffelger-Rabe language, which is that there's a one-to-one correspondence between simply connected one-manifolds and foliations of the plane. Well, that is, there's maybe more foliations of the plane, but if you take the foliations of the plane by lines, and you mine up by some little equivalence relation, and those are exactly correspond to the simply connected one-manifolds. Well, I mean, if you take a foliation of the plane, then by just its space of leaves is a simply connected one-manifold, second countable. And conversely, given one of these guys, you can construct a foliation of the plane. Now, here's some examples, though, to think about. So, for example, here's a foliation of the plane. Now, when we crunch down all these leaves to points, well, these black leaves go down to these 2 points, and here's a whole line of leaves, red leaves. Well, those are these guys, and here's a line of purple leaves and green leaves. Anyway, if you just check out how the topology is, this is being one of the simple examples of non-Hausdorff one-manifold. And, well, here's another example of foliations of the plane. And again, I mean, you have to think about it a little bit, but again, they correspond to a non-Hausdorff one-manifold. I mean, for example, if you look at this point over here, so a little neighborhood of this point, I mean, grabs all of these, well, a little neighborhood of, say, this point grabs sort of all the leaves from this guy that are this guy over, in other words, this guy and up, and a little neighborhood of him is something grabbing, say, this guy and up. So a neighborhood of, in the space of leaves of this black line, this point is just leaves that are, you know, here's a little open interval, and so you can see this is locally this is a one-manifold, not a Hausdorff, simply connected. But these two different foliations give rise to isomorphic, homomorphic one-manifolds. But I just leave this exercise to you that these are really different foliations of the plane.
Why you didn't have to come, for example, to the theorem?
Because there's a little tilde here, just in the corner. I said it real quick that simply connected manifolds are the same as foliations of R2 modulo equivalence relation, which, well, there's something maybe slightly more tricky, but amounts to sort of a little ordering condition, and I mean, it just appears in the guys here as sort of flipping over this Rabe component. So now here's a so I mentioned Palmero before. Let's talk about him again. Here's a theorem of Palmero. So, which is that suppose you have two foliations on a three-manifold. Well, actually, this is a codimension 1 theorem. It's not a theorem about three-manifolds, but let me just use three-manifold words. That's what we're talking about here. So suppose you have a simply connected three-manifold, and you have a foliation, and you have two different foliations in that three-manifold by planes. Then his theorem is that these two foliations are topologically conjugate. That is, there's a homeomorphism of a three-manifold taking one foliation to the other, if and only if their space of leaves are homeomorphic. So so this is really a pretty remarkable one. So in particular, by Heffliger and Rabe Kaplan, if you're given, suppose you have a foliation of a three-manifold by planes. Well, the space of leaves, I mean, manifold being simply connected, we're assuming that, the space of leaves is a non-Hausdorff one manifold. So it can be realized as a lamination of R2, as a foliation of R2. So the point is, if you start with any foliation of say, a three-manifold by planes, well, here's another foliation of a three-manifold by planes which has the same space of leaves, namely, start with the original foliation, look at its space of leaves, and then apply Heffliger or Rabe to find a foliation of R2. With that same space of leaves, just take the product foliation. So Palmeier says, well, these two guys have the same space of leaves, so therefore they're actually topologically conjugates. So you get this really beautiful theorem that if you have a foliation on, say, a three-manifold by planes, that up to sort of change of coordinates, it really looks, when you lift to the universal cover, it looks like a foliation in R2, just multiplied by R. In particular, the universal cover is R3. So here's a little exercise then. That here's these foliations lambda 1 and lambda 2. As foliations of the plane, they're different, but they have the same space of leaves. So by Palmeier, if you just take these foliations and multiply them by R, now you have foliations of R3 by planes. So Palmeier says that when you multiply by R, these foliations suddenly become the same, at least equivalent. So I leave you to check. Leave that to you. So that's it.
Are there any questions?
So tomorrow we're going to talk about taut foliations, in particular the work of Sullivan and Thurston on taut foliations and some constructions on taut foliations.